minutes while I let everyone in. We have the absolute pleasure today of being joined by Stuart Mawditt from SME Water with regards to pressure in water networks. See, I already are failing on the talking and clicking. My name's Claire Withers. I'm chair of the Eastern Area for iWater, and it's my absolute pleasure to welcome you all today. We really pride ourselves on having a very strong sort of network amongst us and all the webinars and events that we run. So we are genuinely delighted with the level of attendance today. As per usual with all our webinars, they are recorded. So if you don't want your camera on, you're not under any obligation to have that on at all. And there will be the opportunity for questions at the end, if you so wish. We will give it one more minute just to get everybody in, and then I'll thank our sponsors and hand you over to Stuart. You just know as soon as I say let's get cracking, there'll be more bleeps. By the way, I can see myself, Stuart. I'm not quite sure that's a good thing.
Oh, on your screen. Sorry, I did a I
definitely have a face for radio, not TV.
There we go.
Fantastic. Thank you.
I was trying to be helpful, so by letting people into the lobby, but I don't know.
Wonderful. Right, so we'll get cracking. So as I said, it is recorded. If you want your cameras on, amazing. If not, we're absolutely forgiving of that. There will be opportunity for questions at the end. And I will just, if you could just go to the next slide, I'll just thank our sponsors, then I'll hand over, Stuart. Thank you very much. So as with all professional bodies, we do massively rely on our sponsors who allow all these kind of events and our in-person events to be such a success. So thank you very much to Claret Civil Engineering, Anglian Water, Merit Skills, Windmill Insight Solutions, Clancy, Kia and RSE. We're utterly spoiled by the level of commitment and support we've got in our area. So thank you very much to all of them. And without further ado, I'll hand you over to Stuart.
Thank you very much. So for those who haven't met me before, my name's Stuart Mawditt. I'm Managing Director at SME Water. I've been working, myself on the spot, I've been working since 2009 and looking at water networks and pressures and flows in the UK and a little bit internationally as well. I've seen a few familiar names pop up on the board of people adding, so I might not be the most experienced pressure person on the network. So do save you criticisms and questions for the end, and we'll head through. Got quite a varied presentation to go to today. So I'm going to talk a bit about the rules that set minimum delivery standards in England and Wales, and why maybe that's not what companies are working to, and why maybe we need to apply a bit more pressure to the networks. Talk a little bit about what affects pressure, why we lose energy as water moves through the network, and how that maybe affects what we do. The benefits of pressure management. We look at the impact. We often look at the impacts of reductions on flows and leakage on networks, and also on the reduction of bursts that occur. So looking at how we look at that as an analysis piece. I'm going to touch a little bit on how pressure data can reveal hidden issues like leakage, unexplained demand and anomalies in the data and network, and reflect on a bit of work that we've done in the past with Severn Trent, but something that's quite a few water companies in terms of using loggers throughout the network to look at things. I'm going to touch on pressure a little bit about what happened and why they're such a critical company to anticipate. To touch on that, I wouldn't say on pressure transients, but it's an area that's increasingly important, and it's an area that we as a business get a bit more, and I know a lot of companies are looking at increasingly. So it's worth touching on and worth discussing. So, starting off with what should we be doing as water companies and as an industry from a water pressure perspective? Ofwat have their guaranteed standard scheme, which sets out what water companies should do, and in that it says water companies must maintain a minimum pressure in the communication pipe of 7 meters static head. Part of the background behind that is the idea that that's the amount of pressure that you would need to deliver water to a loft tank of a typical 2-story house. There's no upper limit to this. So actually water companies can deliver as much pressure as they want to individual customers, but it's in the water company's interest to reduce pressure on the network, because reducing pressure will reduce the flow rate for leakage, and also is better for the pipe network, so reduces burst frequency. So water companies generally want to achieve as low pressure as possible, whilst maintaining what they need to from a customer perspective. One of the key things to note is that 7 meters is to the customer boundary. So when we talk about water networks on the customer side, I've got the blue here is the water company's responsibility. So we have the water main, and then the pipe that goes up to the customer boundary is generally referred to as the communication pipe. Then the orange pipe that takes it into the customer's property is the supply pipe, and that's the customer's responsibility. And then you've got the internal pipe work for the customer. So 7 meters to the customer boundary is effectively up to this point. So my diagram there shows a nice little house, but factors that might affect this is, for example, we might have high head losses in supply pipes or internal plumbing losses. So on the customer side, they might be losing energy as you're going through their network. So just giving customer 7 meters at that boundary might not be good enough for them. Another consideration is long supply pipes and uphill supply pipes. So a farm might be a good example. If you've got a valley and your water main is running through the middle of the valley, and then you've got lots of long communication and supply pipes going off in different directions up the sides of the valley to farms, then giving a customer 7 meters at the end of their boundary might not be enough pressure to then take that water up the side of the hill to get it up to their farm. Other customers might also have contractual agreements in place. So individual industrial users, when they were connected up at various times historically, might have stipulated that they need higher levels of flow or higher levels of pressure as well. So whilst the 7 meters is a standard for households, it's worth considering in other scenarios there might be additional pressure required. The other thing to note on the 7 meters is that typically it's not enough to run a modern home. So often power showers and new modern showers and combi boilers need more than 10 meters, and they're often on a second floor in a building. So 7 meters isn't enough to get water to the second floor of the building, and also to drive things like modern combi boilers, etc. So if as a water company you delivered 7 meters to a customer at their boundary, you'd probably get customer complaints because it wouldn't be enough to satisfy. So water companies typically in the past have worked to a surrogate pressure of 15 meters in the water main. So if we assume in this main pipe that's running through the network, we've got 15 meters, that allows for any head loss that we've got on our communication pipe, guarantees 7 meters at the boundary, and also make sure that that customers are getting that extra bit that they probably need. Looking back at AMP6, we would often have seen companies targeting sort of 20 meters or 18 meters as their standard in the water main as a minimum. And that's because companies would have looked to have balanced low pressure targets as well as improving network performance. So back into AMP and had to report on where they weren't achieving that. As we've moved through changes to reporting and changes to targeting, that stopped being a standard measure for all water companies. So some water companies, as we move through into coming into AMP8, have still choose that as one of their metrics, an optional metric that they that Ofwat can challenge them on. But quite a few water companies have dropped that, and it's no longer compliant. With a greater focus on CMEX, so customer satisfaction rather than necessarily on individual pressures. Current AMP8, we're seeing a much stronger drive to reduce leakage and meet environmental challenges. So one of the things that's really happened since COVID is we've seen much more extreme summers. So we're summers. We're seeing water companies through that period to reduce leakage, to make sure they don't run out of water, a much greater public perception around the levels of leakage that water companies have got, and much stronger targets from Ofwat, which come as part from that customer perception, but also as a part because of environmental constraints on the network and parts of our country which are seeing much stronger supply demand challenges. So particularly over this past summer, we've seen water companies dropping pressures lower and down to 13 meters in some parts of the network. And that's water pressures actually in some parts of water networks. They haven't had a significant number of customer complaints, seems to be working well, and we've seen those pressures sustained through the winter, and that's starting to become a bit more of a norm. So the kind of key takeaway from that is that water companies are increasingly looking to find better margins of improvement, trying to get into areas of improvement that we haven't been in before, and pressure's increasingly important for that. So, key numbers: 7 meters the minimum pressure at the boundary, 15 meters in the water main as a common target, and below that there is a risk that customers might start to be affected, although water companies are pushing those boundaries a little bit. Key considerations: water companies want to reduce pressure to deliver network improvements, particularly around areas like leakage, number of bursts on the water network, and interruptions to supply, which are all key metrics which are increasingly challenging through this AMP in terms of performance commitments. And we're already starting to see water companies not necessarily meet all those performance commitments as they get harder and harder through the year. And these benefits have to be balanced against CMEX. So alongside these drives to improve kind of operational performance, we've got to make sure that customer satisfaction is quite high on the agenda, and also precedents that have been set around areas of the network we've delivered. They might be high buildings that we currently deliver water to, or tall properties, tower blocks, etc. So there's a lot to balance across that. What affects pressure on the water network? So water pressure on the network typically occurs from two sources. So the first and most obvious one is the source of water is at high level. So we have lots of occasions in the UK where we have tanks up on tops of hills, and that's then supplying water down through into the network, and that water then carries the pressure with it. Or we might have pumps or booster stations with key points of the network which are putting more energy into the system for that water as it comes through. As water moves through pipes, we lose energy through friction, and particularly if we've got bends or partially open or closed valves in the network the water travels through, forcing its way through that loses energy and loses pressure. Different pipe sizes and materials cause different energy loss. So generally larger pipes with a higher diameter and plastic pipes which are smoother cause less energy loss, where we've got particularly smaller pipes and rougher pipes like older cast iron, which tends to have quite a rough inner surface. We lose more energy as the water tries to pass through that. The other key factor to consider is that demand increase on a water network means that we're pulling more water through the network, so we've got more friction on the inside, and we're then losing more pressure. So pressure overall will go down. So we often tend to talk about, particularly in summer demand periods, we might struggle for pressure on the network. So a couple of key components in terms of understanding pressure. So looking at total head is effectively the weight of the water acting above which creates pressure. So if you imagine a lake, the total head and the elevation and the pressure, the total head is the elevation and the pressure at a point in the system. So we create 3 points on the network. So at point A, the elevation of that point would be 100 meters, but there's no water pressure because we're on the surface of the lake. So that gives us 0 water pressure and a total of 100 plus 0, which is 100. As we go down below the surface, we then start to get more pressure, but we've offset that with a reduction in elevation. So an elevation here is 75 meters at point B would give a pressure at 25 meters. And then as we head down towards the bottom of the lake, we've then got 50 meters, which is the weight of the water above as pressure at an elevation of 50 meters. And this is true for a static system. So in this case, in the lake, we're not getting water moving through, so we can translate directly the elevation into pressure. So a simplification. If we had a water pipe that was running down this hill, we can use exactly the same assumptions to calculate the pressure at any given point in the pipe, as long as the water isn't moving. So as long as the water is static in that pipe, we haven't got any friction losses due to water moving through the pipes. We haven't got any other losses at all. We can assume that the pressure is related to the elevation in the pipe. Okay, so understanding head loss. So the key component that causes head loss, so the loss of that total head in the network, is friction. So as water moves through pipes, we're seeing the water rubbing up against the edge of the pipe, which creates friction and energy losses through there. One of the key equations that we use to understand this is the Darcy-Weisbach equation, and breaking this down allows us to understand what the key components that affect friction losses in pipes. So the L on the top of that equation represents the pipe length. So you can imagine if we're losing a bit of energy over a short pipe length, if we double the length of that pipe or triple it, we're going to lose twice as much energy or 3 times as much. Moving on through the equation, we divide it by the diameter. So narrower pipes will have more friction. If you imagine that you've got a kind of a small diameter of pipe, the ratio of the surface area that we've got for water to flow through related to the surface area which is touching the outside of the pipe is quite small. As we increase that, we've got a much bigger ratio in terms of the volume of water that can pass through there without having to touch the edge. So the relationship of those friction losses drops. So bigger pipes, less friction losses, smaller pipes, bigger friction losses. Faster flows cause a big increase. So obviously if the water's moving faster through that pipe, then we then get much higher friction losses. And that's a square. So that means that as we increase the flow through a pipe, which is represented by the velocity there, we're then seeing a square relationship in terms of improvement. So putting twice as much water through a pipe will create 4 times, with 4 times being the square of 2, the amount of head loss that we'd see in that pipe as we're trying to force more through. And then the last component there is the roughness of the pipe surface. So as I mentioned earlier, plastic pipes tend to have very smooth surfaces. Where we've got older cast iron, we get tuberculation and breakdown of the pipe structure on the inside of the pipe. So you tend to get much rougher pipe surfaces. That tuberculation can actually make the pipe smaller because you're getting that material building up and bulges in the pipe, which then mean that actually you're getting a double effect, that you're getting a rougher pipe surface and actually it's making the diameter narrower, which then gives you a smaller area. So those things all contribute to us getting a higher head loss in a pipe. And one of the key takeaways when we're looking at water networks is effectively the bigger plastic pipes have fairly negligible levels of friction losses on them compared to older cast iron networks. So narrower, rougher pipes have a higher head loss, and higher flows create a higher head loss. The other area is looking at turbulence in pipes. So on the left-hand side, we've got what we'd call laminar flow within a pipe, where we've got waters moving in nice smooth layers, and it's not interacting with each other. As we come across parts in the pipe which are causing restrictions, the water has to go through that restriction, which causes friction losses, but then also it can create turbulence within the network, which means that we're losing energy as the water effectively bumps into each other as it moves around. And that turbulence can be caused by corners in the networks, where the pipe work is actually going around a bend or in a corner, or where we've got other lighter bends in the network, or where we've got partially open or closed valves, etc. within the network. That can have quite a significant impact. Moving on to talk about benefits of pressure management, on time. So the relationship between leak flow and pressure typically uses the formula flow equals pressure to the power N1. So as we increase pressure in the network, the flow that's coming out of leaks will increase, and we use an N1 relationship. And I'll talk a bit more about that N1 relationship. And that N1 relationship depends on a number of factors. So really what I'm talking about here is I've got a burst on a pipe, and that burst can have a number of different failures. It could be circumferential, it could be longitudinal, it could be corrosion, so it could be a hole in a cast iron pipe, it could be a joint, and with those joints they might open up as we increase the pressure. So depending on the type of failure can affect the relationship between flow and pressure. We've also got the surrounding material to consider. So where we've got where the burst on the network can start to erode the surrounding material around the pipe, and that might cause the pipe to fail more and open up more. It might also mean that it's not then restricting flow that's coming out of the pipe. So these lines on the graph represent different N1 values. So an N1 value in the blue is a value of 0.5. So effectively showing the relationship between if we put the pressure to the power 0.5. So as pressure increases, the flow doesn't increase proportionally. And then N1 of 1 is effectively putting something to the power 1 just means you get the same result. So as pressure increases, the flow increases proportionally. And an N1 of 1.5 means that as we increase pressure, the flow increases at a much faster rate. So N1 uses a fixed orifice equation. So in this example, we're saying that actually there's a hole in the pipe and that pipe doesn't change. So this is an experiment which I remember doing as an undergraduate at university. And the idea behind this is that you fill a reservoir with water, you've got several holes, and these are all fixed orifice holes. So the size of the hole doesn't change as you do the experiment. As you go down through the water, you've got higher pressure at the bottom because you've got a greater weight of water, so you get a stronger jet at this point. But what happens in this example is that the more water and the higher pressure you've got, the more you try and force water out of here, the more energy it loses. So actually the jet doesn't travel as far as you might expect it to as you come down. And this relationship is proportionate to the pressure to the power 0.5. So we're getting diminishing returns in terms of the pressure for the length of the jet. And this is consistent with cast iron failure, where we get a hole appearing in the cast iron. So you can see there in these cases there's a hole, and actually that hole doesn't change in size depending on what you're doing. So this uses a kind of a cast iron spot failure, typically follows this line. So we're not seeing a proportional representation in terms of the change of pressure and flow. A 1.5 assumes a variable opposite orifice. So this is the opposite. So effectively there you can see a plastic split in a pipe that's been excavated. Now you can imagine that that split opens up, and as the pressure increases in the pipe, actually that split probably opens up a little bit more and a little bit more and a little bit more, which allows more water to escape. So that's giving us a variable relationship. So a good example of that would be a plastic operational. Now there's other types of pipe failure that then maybe sit in between. So there might be joint failures or circumferential, which are maybe allowed to open up a little bit, but are then maybe more restricted. And what we often find is that on water networks, we get a mix of relationship depending on the type of network. So we might have a network that's predominantly cast iron, and we might have a network that's predominantly plastic. But these relationships allow us to calculate the benefit that we would get from reducing pressure on a network. The other key thing to look at is bursts. So the number of times that the pipes fail on a water network. So a lot of practitioners apply a typical value of burst equals pressure to the N2, where the N2 is 3. So effectively a cube relationship. So you can see on that graph you've got burst per 1,000 properties against average zone night pressure, looking in an area, and the relationships on there. What we often do is try and split burst down, and this is getting a bit complicated, but into non-pressure dependent bursts, and then pressure dependent bursts. So the idea that we've got a block of bursts at the bottom of the graph here, where we're saying, regardless of what we do with pressure, that pipe's always going to fail to some extent. And that might be because of ground movement. Particularly, we've seen a lot of the past 5 years of very dry summers, so we might see ground shrinking. We then get very wet winters, so we're then seeing ground expanding. And depending on the soil type, you're then seeing different types of relationships, pipes. So we often talk about a non-pressure dependent component that sits at the bottom of the graph, and then we've got this power law that then gives us this relationship, with this typically using a value of 3 to represent that power law. The alternative to this is Alan Lambert, who's probably a godfather of pressure and bursts in the water industry. I'm sure you won't mind me saying that. His straw that breaks the camel's back approach. So actually, it assumes that there's a mechanical failure point in the network. So this, we've kind of got a curve there that shows a cube relationship. But if you look at that graph there, you could take a cube relationship from it, or you could say, well, actually, there's just a point at which it fails. So there's a point at which you get negligible bursts, which is representative of that non-pressure dependent, and then you get a failure. And actually, there's lots of things that affect the network once it's been laid. So things like soil corrosion of the pipes, so cast iron pipes that are laid in clay will often corrode quite viciously. You get traffic loading on networks. So if you've got pipes that are laid under roads, you've got movement in terms of what's happening. You might have pressure transients happening on the network. So customers operating and closing valves, or water network pumps that are then damaging the network as they pass through. So that gives us an external factors that bring the actual strength of the pipe down to here. So if we can bring the pressure down to a point where we're down below that point on the network, we're then achieving a point below where that mechanical failure is. So there's the suggestion that actually, rather than us continuing to get benefits from pressure reduction, we actually reach a point where we're getting diminishing returns. And that's quite interesting when we start talking about those lower ends of the pressure scale. So once we're below 20 meters and water companies are trying to balance that, do we keep reducing pressure? Where can we see benefits compared to making sure we're getting a good customer satisfaction levels and not impact on customers' homes? One of the other things that's talked about in the industry is understanding about whether networks, once you've reduced the pressure on a network, a lot of people talk about the idea that the network then relaxes and becomes accustomed to that pressure. So over time, the level of bursts build up. So this is some examples. So this is examples of pressure reducing valves that were installed and commissioned. You've got about 49 schemes there that were installed between 2010 and 2013. So normalizing that, you can see you've got quite a significant impact. And this is looking at annual service pipe bursts per 1,000 connections in those areas. So you can see that you're typically getting 5 service pipe bursts per 1,000 connections in the years before, and that's dropping down to sort of 2.5. So you're halving the number of service pipe bursts happening on the network. So that's looking at PLO installation. Commissioning might come into second year, so it might take a couple of years to kind of get that to the point where the system's working effectively. So 5.3 before, and then 2.5 bursts afterwards. Just looking at the 2010 schemes, we then did a bit of analysis over the next 7 years. So you can see in that example, you've got that sustained burst reduction benefit. So from the analysis we've done, we haven't seen that the network then starts to creep up to previous burst levels if that pressure is sustained. But there's certainly other people in the industry who think it does. So there might be questions around what benefits you're going to get from pressure reduction and whether that's sustained over a longer period. Okay, going on to talk a little bit about using pressure data within water networks. So how do we identify opportunities to optimize pressure on our networks? I'm going to talk a little bit about installing pressure reducing valves and how that allows us to reduce the pressure, and property pressure analysis, which is just one of the tools that we use as part of that. And then I'm also going to talk a little bit about dynamic pressure modeling, which is effectively using pressure sensors on the water network and looking at the relationships between them to understand what's happening. So pressure reducing valves allow water companies to manage the pressure on their networks. So if we've got an area that's high pressure, we can put a valve on the network, and a pressure reducing valve can either give us a nice steady sustained pressure on the outlet of the PRV, so we can drop by a fixed amount and we can sustain the level, or we can also do quite complex controls on there, which allows us to say, well, at night time we want to reduce the pressure further, but then on a daytime when people start taking water from the network and we need more pressure available, we can start to increase the pressure as the flow increases. So this is effectively looking through a cross section of an area. We've got properties there with elevations. So you can see there we've got ground level, we've got a number of household properties, and we'd set up a target property head. So in this case, we've put that at 20 meters. We might do that at 15 meters. We might do that at 30 meters if you're looking at how you could really squeeze pressure down. We talked earlier about our total head. So we've got our total headline, which represents the pressure plus the elevation in that DMA, and we can see that that's decreasing as we go through the area. So as we're moving through the water network, we're losing energy and we're losing that total head. We can then simulate the impact of installing a PRV. So we can see there we've dropped the pressure down, we've put a valve on the network, and that effectively just drops it down as a straight line. So we've got a parallel line which shows the reduced pressure going there. With that then comes down to a point in the network, which is our restricting factor. So in most domestic water networks, we'll have a restricting factor, which is the high point in the area where we've got very high head losses. So where that line's really steep, it might be a far point in the network, but we can pick up where we've got those restrictions. What we can also consider is different scenarios. So in this case, that might be our peak flow. So that might represent the amount of head loss that we're getting in the network on a morning when everyone's up, everyone's having their showers, everyone's getting ready to go to work. We might have a minimum flow scenario. So we talked earlier about the head losses in the network and identified that at lower flows on the network, we're then seeing less head loss. So you can see that isn't that's a much shallower profile. Adding that model, which is allowing the PRV to change its outlet pressure at different times of the day, then we can achieve a reduction at minimum flow. When we look at that from an overall benefit, you can see we've got optimization at that point. It comes from a reduction, which from the formulas that we looked at earlier in those graph reductions, we can say we get a reduction in pressure, a reduction in flow and on leaks, and a reduction in burst rates as well. What the variation in pressure that we see through the day and what the impact that might have on the network. So you can see previously the properties at the end of the network are getting a variation between their nighttime, the blue pressure, and their peak morning pressure there, and actually those reduction. And one of the things that we often find from customer complaints is that customer complaints tend to come more from where customers are seeing big variations in pressure. So where maybe they're getting a real high pressure, a real low flow, a real high flow at times, and then it's varying to quite a low. Whereas actually, if customers have got quite a sustained pressure, they tend to be fine.
Sorry, Stuart, if you can hear me, your Wi-Fi's gone a bit funny. You keep cutting out in really good bits.
Oh dear. Do you want me to go back over any of it? Where did I get up to?
I think it's only been a little bit intermittent. It probably just the end of the last slide would be really helpful if that's all right. Thank you.
Yeah, I'll tell you what, I'll just go back to this bit. So we simulate the impact of installing the PRV. So that's a peak flow scenario. So we less on the network, so we've got less head loss. So we've got a slightly shallower line in terms of what's happening. So when we take that from our PRV, we can show that at night time we'd have excess pressure. So those properties there, where it might be optimized during the day, it's not as optimized at night. Now, the control that we have on pressure reducing valves allows us to modulate that valve and give greater reduction at minimum flow. So we can then say, well, let's squeeze the pressure down a bit more at night time. So that reduction in pressure gives us reduced network. So where we're seeing significant variations in pressure.
Sorry, it's a very intermittent signal.
I'll tell you what, let me just stop sharing for a second. I shall just try plugging into a different network and see whether that improves. My camera might go a bit odd. You might see me on our meeting room screen for a second, but I'll switch back. Is that any better?
Let's go with that, and then I'll do a hand signal on the screen if it cuts out.
All right. I might not. Oh yes, I might not see you, but if I'm sharing, but we shall persevere.
Thank you.
I shall just have to reshare 2 seconds. Sorry, my computer's just still reacting to me plugging in. Okay, right. I shall persevere. Apologies if it's breaking down a little bit. Right, so we've got another sort of 5-10 minutes left. Right, so I'll move on from this bit. The key takeaway is that we're getting network calming, so reduce. There was a bit of an anecdote that I don't know whether you caught, that customers tend to prefer calmer pressure. A lot of customer complaints come from normally stem from rather than sustained low levels of pressure. So yeah, if you can get customers to a good level of pressure and keep it at that point, they tend to be happier overall. Okay, so moving on to some additional insights. I'm going to talk about a project called Dynamic Pressure Modeling we did with Severn Trent, where pressure sensors are deployed in areas to help understand existing network conditions and react to bursts on the network. So in this case, we've got a district metered area. So district metered areas are used by water companies on their clean water network to create a subsection of the area. And what we typically do here is we monitor the flow going into an area. We close all the valves around the outside, and that allows us to understand what's going in, and we can subtract how much demand is being used by customers, etc. And that allows us to say, well, whatever's left, in theory, should be leakage. And if that changes, we then know we've got bursts on the network and we can respond to it, and we've got a fixed area that we're responding to. So in this example, you've got a burst, 3 meters cubed per hour burst in the area. The red dots on the network are DPM loggers, so they're pressure loggers that were specifically deployed. The analysis then generates an area of interest. So we're then able to say, here's a part of the DMA where the burst is, and the leakage teams are able to go out to that. So rather than looking in the whole area, which is the orange boundary, they're able to go and investigate that. And that works because of the head loss on the network. So when we see that burst occurs, that increases the flow. We then see an increase in friction losses through the pipes. So we see a drop in pressure in that area predominantly compared to the others. So we're able to pick that up. And this is something that is increasingly being used by water companies. So we see some of the companies, Angling Water, Affinity, have installed increasing numbers of pressure loggers on their water networks. Some people are doing more complicated things around hydraulic modeling, so actually building detailed models that simulate the head loss in the network a lot more effectively. Other companies are doing more simple things, just looking at what the difference in pressure is without getting into too much hydraulic detail. So it's quite a useful. The key thing is that it's not applicable in all areas. So where you've got cast iron networks, you've got rough pipes, you've got small pipes, you get a very high level of head loss, a very high change in pressure when you get a particular flow. So that makes it very effective as a tool. Where you've got more new plastic networks and bigger pipes, and you're not expecting to see changes in pressure as a result of flow, then you're often not going to see that impact. So when you get a flow on the network, the pressure doesn't change too much. There isn't that much to investigate. So it's very much suitable in some cases, but not necessarily suitable for all areas. This is showing some of the results from Severn Trent, and they found that leaks were then found 30% faster in areas with dynamic pressure modelling, so quite a good result. So looking at leak detection efficiency over a longer period of time, and 50% more leaks found in DMAs with that solution in place than areas without. So it can be quite effective, but it needs to be deployed in the right area. It's not formed part of Severn Trent's long-standing process. I think with all solutions, you've got to look at the overall cost benefit and the challenges of deploying pressure loggers on the network, maintaining them long-term means that there's probably there might be more cost-effective solutions out there in terms of what's done. It can be quite effective for doing things that are non-leakage. So particularly identifying where you've got boundary valves open with adjacent areas. Pressure can tell you where you've got inline valves. So you've got part where you've got valves in the network which are closed, which are then causing restrictions. Might also highlight where you've got problems with your GIS. It's quite good for identifying demand anomalies. So picking up where you've got unknown customers on your network or unknown connections, because it's effectively telling you what's happening without you having to, which you would be limited from if you were just servicing your known network. Good example of this is the analysis picked up a kind of a leg down in this DMA, so an area fed from the top. You've got allotments down here. You've got a valve that was previously open that had then been converted cove at the top. So looking at these allotments, you've got possible connection locations coming in. Did a survey, they found that actually there was a meter that had been installed that fed the allotments from a different set that hadn't made it through into the GIS and the analysis. So there was additional demand in the area. If you were looking for that as leakage, you wouldn't necessarily survey that and think, oh, there's anything wrong here. But by doing that balance of where should the water be going and where is the water going, you get a different picture. So how do I identify opportunities? So looking at installing PRVs is quite effective. Dynamic pressure modeling can be quite effective for understanding anomalies, but it only works where there's high head losses, so the diameter cast iron networks. Just talking a little bit about pressure transients. So pressure transients, also known as water hammer, generally occur where a column of water suddenly. So typically, if we've got a volume of water in a pipe and that's moving from the pipe, if we close something like a valve very quickly, you can imagine you've got the weight of that water comes crashing through into the valve, and then the energy then bounces back through the network. So there's a shock network which can cause damage to assets. This typically occurs on water company assets, so for example, pumping stations, or might be PRVs that are opening or closing too quickly. It could be network operations. So a typical customer example would be if a customer's got a tank as part of their operations, and they've got a solenoid valve on the inlet to that that's then controlled by level. So they open that up, the tank's filling at a very fast rate. It hits a point, and that tells the valve to close. The closed valve closes instantly, and that sends that shockwave back up the network, which can cause instantaneous bursts and damage network assets on there. And that damage can be around PRVs and other network control assets as well. In AMP6, we saw an increased development of higher quality logging equipment. So a lot of the kind of the previously, historically, we've seen water companies either taking spot readings of pressure or monitoring the average over a 15-minute period. But we increasingly see transient loggers emerging in AMP6 with logging typically of 100 hertz, so that's 100 times per second used to pick up transient waves. That really is an effect of, I think, technology prices kind of reducing, and that technology being much more widely available for the water companies to deploy with battery technology as lift and shift loggers and permanent logging on the network. Full impacts of transients aren't really fully understood, and that can make it quite hard for companies to build business cases to say, I can see there's transients happening on the network, but how do we understand the kind of the benefit of resolving them would be? And particularly where we've got pumping stations, those impacts can be quite significant. That's just an example there showing that at the top you've got transient data happening on a network, and as I said, that's sort of sampled at sort of 100 times a second. If we resample that over as 1 minute data, you can see you're immediately starting to smooth that out. And a traditional 15-minute sampling of that data just wouldn't show any of the transients that's happening over there. One of the things that are emerging really this AMP is this move from 15-minute as standard across network assets to moving to 1 minute data with minimum and maximums. So typically we might sample at a second interval. We'll then summarize that data to say what's the average over that second, and then what's the minimum and maximum, and using that data rather than the more detailed transient data, which is more cost effective for logging. It's more costly for logging. It's more costly for us then to share that data as water companies. So an example there of a pump, you can see on the graph, you've got the flow through the pump, and the pumps are turning on and off. You've got lots of transient activity around particular times when the pumps are coming in and out, turning off. This is an example where then the pump operations were changed going into 2022, and you can see there's a significant reduction in transients in that period. So the number of transient events that are happening. You've still got more significant events still happening, so there's still more work to be done on those pumps, and often it's those big shut and shut-offs and starts. Last bit, why are transients so important for water companies in AMP8? So interruption supply is a key challenge for many water companies as targets get tighter, and interruptions to supply for water companies are measured in terms of property minutes. So if we have a big event on the network that takes a lot of properties offline for a large period of time, that can be an entire water company's interruption supply for the year, or that one event can mean that they've missed their target completely. So the actual large-scale failure of bigger assets is under increasing scrutiny as we move forward over the next couple of years. So more costly interventions to maybe improve pumping on the network are starting to get a bit more palatable, I think, from an expense perspective. Burst and leakage targets mean water companies need to start tackling some of the less cost-effective options they have available to improve performance. So rather than necessarily looking at how do we find leaks and mend them more effectively, we maybe need to look at how do we prevent bursts happening the first time, and that might mean challenging customer side usage and some of their own assets. And then we're also seeing logging technology is increasingly more cost effective, so allowing continuous monitoring and understanding of what's going on in the network. Okay, any questions? I'll just stop sharing my screen and then I can see the teams again. How are we doing, Claire? Did the sound pick up?
Yes, it was a bit better. It was just the odd word that we kept missing, and I was conscious that when we were getting into the detail, they're the bits we probably want to capture. But Joshua's given us a question, so thank you, Joshua. Do you think that there is rationale or evidence to say that due to pressure management, we're making it far more difficult to find leaks?
Hi, Josh. Josh is an expert in this field. Well, I think he should be telling us the answer himself. I don't know. I mean, one of the arguments for this would be that if we're reducing pressure on the network, we're making leaks quieter and harder to hear. But there's no evidence that I've seen that suggests that whilst if we reduce the pressure, we make the leaks quieter, but it's the loud leaks that are the bigger ones. So often the smaller leaks and quieter leaks can be large leaks that are difficult to find anyway. And I think we're seeing big improvements in terms of the acoustic technology that's available. There's a lot of AI and improved analysis of acoustic data and improved listening. So whilst maybe traditional listening stick approaches might be harder, I think there are solutions out there that can maybe listen a little bit more effectively to what's happening on the network. I think one of the risks we have with pressure management is we see an area that's got a large level of leakage and we reduce the pressure, which reduces the flow rate from that leak. I think what we need to be mindful of doing is making sure we go out and find the leaks as well. We don't see it as a solution to that leakage problem, because actually there should be leaks out there that we can find, and we should be using pressure management more to reduce the occurrence of leakage and bursts on the network and maybe sustain asset life.
Do we have any other questions in the room? Okay, while people have a think, it'd be interesting to know customers' interpretation of when we dig up what effectively looks like an absolutely fine road to repair a leak, because we have done that investigative work beforehand and spotted that there is a problem, but it's not visible to the customer. What are your thoughts on this, Stuart?
I think one of the challenges we have as we move through so as a bit of background on leakage, back in AMP6, water companies were very much targeted around the cost of water coming into their network. So some of the water companies like Northumbrian Water might be a good example, where they've got big upland reservoirs. Actually, they've got a cheap source of water. So actually, they weren't really pushed to find more leakage on their network because they could just continue to put reliable water at the top end of the network. Whereas some of the more southeast water companies, where you've got more expensive water sources, you've got more challenging supply-demand conditions, abstraction licenses, etc., then had to do more. We're now seeing, as we go into this AMP, that all the water companies are being challenged to reduce the amount of leakage that they've got on the network, which is driven more from the regulator and customer perception in some cases. And one of the big areas that we need to improve is how do we identify leaks that are going to become bigger leaks on the network. So one of the things that acoustic logging and some of those technologies are giving is awareness of leaks. So we might start digging up the road to repair leaks that are actually fairly piddly little things, because we're interested in getting to them before they become bigger leaks. Now, there's a huge challenge to say, well, how do you know which ones are going to get worse? And I don't think people necessarily have the answer to that at the moment. But yeah, there might be scenarios where we're digging up roads and causing disruption because we're trying to get to increasingly smaller leaks, but ones that might go wrong.
Super. Kirsty Ayres has come in now. Given the need to reduce consumption and save water, should the conversation move more towards using pressure management to reduce DI rather than focusing on leakage?
Yeah, absolutely. And that's, I think, a lot of what we saw in the summer was where water companies were seeing things being a bit more stretched from a supply-demand perspective. There was temporary measures to reduce leakage, but then also one of the areas that we don't understand as well is impact on customer demand. So actually things like obvious examples would be where you've got a toilet cistern and you've got a float valve in there, that actually if you've got lower water pressure on your network, the toilet won't fill up as much, because actually the float valve will reach a point where it closes the valve, and that's acting against the pressure of water coming into the network. So changes in pressure can have material impacts on those things. Obviously changes flow rates from taps, from hoses, etc. So you're actually, if you're washing your hands under a running tap, you'll be using less water if the pressure on your network is low. But I haven't seen a huge amount from the industry that says if we reduce pressure by 5 meters, we get this level of reduction in customer demand. So it's a good area that needs more exploration, I think.
And now Anna Reeves has said, would you say that using measures of transient pressure would give an indication of a risk of potential no water supply versus measuring the pressure on its own? I think that pressure management is more of a control measure for controlling the pressure related bursts.
Yeah, so I think the kind of formulas that I showed up there was relatively simple formulas showing the relationship of pressure and bursts. I think they're formulas that have been derived over probably the past 50 years, and really a simplification of, well, if we change pressure, what benefit do we get, to allow people to kind of implement things. I think the impacts of transients aren't as well understood, and I think we can drive better understanding and kind of business cases to kind of further that from the impact it has on bursts and the impact it has on leakage. But interruptions to supply is such a big factor as we go through this AMP that, yeah, it'd be good to see that coming more into the business case in terms of what's happening.
Lovely. Everyone's obviously had a think because the questions are flowing in now. So you discussed minimum pressure thresholds such as 7 mil head and 15 head. From an operational perspective, what maximum pressure levels are utilities typically comfortable operating within distribution networks?
So you do see really high pressure networks, which might go up to 100 meters. A lot of that has been taken out these days. So I think going back 20 years, you might have seen that. But certainly as we go into distribution, so you might have higher pressures on the trunk mains, and then as you move into distribution networks, you typically see less than 30 meters on a water network. What you might see is that variation between daytime and nighttime. So in my example where I showed the properties with the elevations and you could control the pressure there, if you've got a situation where actually you've got another area downstream and another area downstream, you might be needing to maintain 30 or 40 meters pressure in this upstream DMA, so that as you move through the network, you're then losing another 5 to 10 at each stage. But yeah, I'd be surprised to see much more than 30 or 40 meters on a water network.
But the only thing we haven't covered is if it's incredibly high pressure, fittings start flying off, don't they?
Yes, I mean, there's an argument that says, well, if the network's used to that pressure, there's this kind of, not an area that I'm completely confident in, but there does seem to be a lot of, well, the network gets used to this pressure, and if you reduce the pressure, it just gets used to this new pressure. But I haven't seen much evidence of that.
I think we've got time for one more. Is that it's an additional question to the one that was already just been asked. Is that maximum pressure mainly determined by customer service considerations or by leakage and burst risk?
I think most water companies in the UK have gone quite hard on the easy wins from installing pressure management on the network over the past 20 years to reduce pressure and get the benefits, the easy wins really from burst reduction. I think where you've got higher pressures on the network, they're typically because you've got flats and other things, which mean that you've got to provide an additional 20 meters on top of what you'd normally provide. We have seen cases. Thames Water did quite a big project, probably going back 5-10 years now, where they went through and actually installed boosters on higher rise buildings so that they could reduce the network pressure and create a new normal of, we're going to install a small booster for you, and then handed over ownership of that asset to the owner of the property so that they could then calm their networks down. I think the Thames have probably got parts of the network which have got lots of big buildings in and lots of very high buildings, so making sure there's but that potentially could cause additional problems, because if you then got lots of customers with lots of pumps and lots of activity going on, you're potentially causing transients on the network. So there's maybe trade-offs between us calming pressures down in some areas and then boosting and making our networks more complicated, which potentially causes transients but reduces overall pressure. So yeah, there might be more to come over the next 10 years around some of the impacts of that.
Brilliant. Oh, I think we're going to have to save your question, Andrew, because otherwise we're going to run over time. But I'll make sure Stuart gets the question, and
I can answer that one quickly if you want.
You sure? Okay.
Yeah, the water company doesn't have to provide pressure. I think the key thing is where you've got where you've maybe set a historical precedent. So where you've got a building that you've been providing pressure to for the past 50 years, if you suddenly reduce the pressure and people go without water, that's obviously not great from a CMEX perspective. So yeah, it's managing those risks out.
Brilliant. Well, thank you very, very much for your time, for Stuart, and for everyone that's attended today. It's been a pleasure to host this webinar today, and have a lovely rest of your day. If you have enjoyed this session, please do have a look at the other Eastern area ones that we've got up for offer at the moment. We have at least half our year's programme advertised currently, so there's plenty of choice and variety. Thank you once again. Have a lovely afternoon, and get out and try and enjoy some of this sunshine that feels a long time coming.
Thank you.
Thanks, everyone.